Section 6.1, example 1, finding the interval and radius of convergence. So for each of the following series, find the interval and radius of convergence. So with this first example, to find the radius of convergence, what we're looking for is what values of x are going to make this converge if possible. So looking at this, I think it'll be easiest if we did our ratio test. So for the ratio test, we let rho equal the limit as n approaches infinity of a sub n plus 1 divided by a sub n. So the limit as n approaches infinity of the absolute value of, I'm going to do keep change flips, so a sub n plus 1, and then I'm just going to multiply the reciprocal. So a sub n plus 1, we have x to the n plus 1 over n plus 1 factorial. And then we're going to multiply the reciprocal of a sub n. So reciprocal, this is going to be the numerator, and factorial, and this is going to be the denominator, x to the n. I feel after the last section or the last chapter, we're kind of experts at this one. N approaches infinity. Let's adjust this because I see that we could divide out an x to the power n. So I'm just going to separate these two. So x to the power n times x. And I'm going to remove the first term of this denominator. So in the numerator, we have x times x to the power n. And then on the other fraction, we have n factorial. And still absolute value. N plus 1. N factorial x to the n. And a lot of this stuff ends up dividing out. X to the power n and factorial. So the limit as n approaches infinity of the absolute value of x over n plus 1. And now as n approaches infinity, the whole thing, the whole denominator gets really, really large. So large that we consider that value to be 0. So here this is equal to 0. And if you remember our ratio test, rho being between 0 less than or 0 less than or equal to rho, let me actually write it down. 0 less than or equal to rho less than 1 implies convergence. So this is going to be converging for all values of x. We don't have to restrict anything. So converge, or we could say a sub n converges for all values of x. For all values of x belonging to the real numbers. And there we go. That's the first one. Let's take a look at the next one. Hopefully we could use the same thing. That was pretty easy. And because we have that n factorial, it looks like we could apply our ratio test. So coming up here, again, we have rho is equal to the limit as n approaches infinity of a sub n plus 1 over a sub n. What I'm going to end up doing is a sub n plus 1 times the reciprocal. Oh, well, we don't have any fractions here. We could just do it in the same line. So n plus 1, so n plus 1 factorial x to the n plus 1 over n factorial x to the n. Limit as n approaches infinity. Let's do some factoring. So let's get rid of the first term here and separate these two. N plus 1 times n factorial x times x to the power n. And we have n factorial x to the n. x to the n's divide out, n factorial divides out. The limit as n approaches infinity of the absolute value of n plus 1 times x. And as x gets larger and larger, or as it approaches infinity, this whole thing approaches infinity. And based on the definition, if rho is greater than 1, no, well, one of the parts state if rho is equal to infinity, then the series diverges. So a sub n diverges for all x belonging to the real numbers. So we can't do anything with that one. So we have to say it diverges. There is no interval for which it would converge. All right, looking at this one, do we have enough room? I think we have enough room. All right, could we use, let's see, could we use it? I'm going to do again, because we have, well, we don't have like n factorial, but I think we could still use rho. We could still use our ratio test. So we're going to take the limit as n approaches infinity of x to the n plus 1. So we have x minus 2 to the n plus 1 over n plus 1 plus 1 is going to be n plus 2, 3 to the n plus 1. And we're going to multiply the reciprocal. So n plus 1, 3 to the power n over x minus 2 to the power n. Clean it up. So we have x minus 2 times x minus 2 to the power n, n plus 1, 3 to the power n. Denominator, we have n plus 2, 3 times 3 to the power n, x minus 2 to the power n. X minus 2 to the power n, those divide out. 3 to the power n divides out. And let's see what happens when we clean it up. We have x minus 2 times, oh, so one thing I do see are these n's. So we could multiply by 1 over n to the top and bottom. So that's going to be 1 plus 1 over n. That's a whole numerator, and denominator we have 1 plus 2 over n times 3. And now as n approaches infinity, we have, actually we don't have to write this part. As n approaches infinity, this part goes to 0 and this part goes to 0. I don't see n anywhere else, so what we're left with is the absolute value of x minus 2 over 3. Because here, as this goes to 0, we can multiply this in here. As this goes to 0, we can multiply this in here. So that's what we have left over. And now, if you remember correctly, we have rho. So 0 less than or equal to rho less than 1 converges. So we're going to let rho equal this right here and see what we end up getting. So absolute value of x minus 2 over 3 So any value larger than 0 is going to equal, or any absolute value is going to be larger than 0. So we could kind of ignore this side. And what I'm going to do is set this less than or equal to, and at the end, we'll see where these values converge. So we have x minus 2 over 3 less than or equal to 1, or negative 1 less than or equal to 1. Negative 3 less than or equal to x minus 2 less than or equal to 3. And plus 2, we have negative 1 less than or equal to x less than or equal to 5. So now we might not converge at these 2 points. So what we're going to do is test these 2 points to see what the values end up being. So let's look at those two, kind of see the whole thing here. So what we're going to do is let x equal 1 and see what we get. So here it's going to be 4x equal to negative 1. And what we have is the sum as n goes from 0 to infinity. Negative 1 minus 2 to the power n. Notice that this 3 is also to the power n, so why don't we just do that? So negative 1 minus 2 over 3 to the power n. And we have 1 over n plus 1. So does it converge here? It looks like this is going to be a negative 1 to the power n, 1 over n plus 1. So here, this does converge. And we know that from the previous chapter. I believe it was one of the ones that we tested. That was for x equaling 1. And now let's see if it converges for x equaling 5. Is it 5? Yeah. So for x equaling 5. So the sum as n goes from 0 to infinity. 5 minus 2 over 3 to the power n. 1 over n plus 1. So 5 minus 2 is 3. 3 divided by 3 is 1. 1 to the power of anything is still going to be 1. So all we have here is our n plus 1. 1 over n plus 1. And this actually diverges. So now our interval of convergence So our interval of convergence is, we do include negative 1, we do not include 5. And that's it. If you have any questions, please feel free to ask. Otherwise, bye.